Hello and welcome to this tutorial on how to generate simplified lifecycle assessment models for geothermal energy systems. It relies on the development from the GEOENVI project, which is a European project aiming at tackling the environmental concerns for deploying geothermal energy. On the one hand, it aims at answering environmental concerns in both impacts and risks, by first setting an adapted methodology for assessing environmental impact, and on the other hand, by assessing the environmental impact. And to tackle the part on assessing the environmental impact, a team of different partners, MinParisTech, CSGI, Vito, and OS, developed first guidelines to help in the generation of lifecycle assessment models of geothermal energy technologies, and second, simplified models and a protocol to develop them to facilitate the multi-criteria environmental assessment of geothermal projects. Just a brief reminder, lifecycle assessment is a holistic, multi-criteria standardized tool that estimates the environmental impact of a system or product over its entire life cycle. It's based on 4 different steps, and it requires a very good understanding of the system that is studied, as well as of the methodology to be applied adequately. And it's then a very powerful tool to make decisions when we compare, for example, different energy generating technologies. But it can be very cumbersome to apply. So that's why we developed this protocol that enables LCA practitioners and experts in geothermal systems to develop simple models that rely on a small set of parameters to estimate multiple environmental impacts from this set of limited parameters. So in the following, I will show the application of the 5-step protocol. So this application is meant for LCA experts or geothermal practitioners with some knowledge of lifecycle assessment, and ideally with knowledge in the programming language Python. So first, what are those simplified models? Well, they are simple models. There are arithmetic equations that rely on a small number of parameters that can estimate one environmental impact of a specific installation. In our case, we're looking at geothermal installation. It's a 5-step protocol that I will go through in this presentation. So in the following Jupyter notebook, so this is the environment you are seeing here. It's called the Jupyter notebook. I will give indication on how to apply the protocol for a hypothetical geothermal installation. But before diving into those 5 steps, I just want to explain a bit more what this Jupyter notebook is and how we are using it, and the 2 different libraries that we are using, namely Brightway 2 and LCA algebraic. So I already mentioned that this work relies on the Python programming language, which is an open source language which includes thousands of different additional libraries. And in this presentation, we will use the Anaconda distribution and 2 different libraries, Brightway 2 and LCA algebraic. Brightway 2 has been developed to do lifecycle assessment computation in Python, and it was developed by Chris Mittel. And LCA algebraic is a library that was created above Brightway, so it relies on Brightway, and it's designed for the definition of parametric inventories to allow a fast computation of lifecycle impact. And it's especially suitable for Monte Carlo analysis. It has been developed by Raphaël Jolivet. You can find more details on the 2 links that you can see here. This script will be available on the GEOENVI website, so you will be able to click and copy those links. So the installation of Brightway 2 and LCA algebraic is facilitated with the installer that you can find on the following website. So once you have installed everything, you will simply have a shortcut for Jupyter on your desktop, and you will be able to open a Jupyter notebook as you see it here. So Jupyter notebook, what do I mean with that? So basically, it's the environment in which you will be coding, in which you will be generating your simplified model. It allows you to define markdown cells. So if you click on this cell, you can see here it's highlighted in blue. It's a markdown cell, but you could also define it as a code cell or a title or a text. but let's keep it as markdown. And once one cell is selected in blue, you can simply navigate through them by using the arrows. You can also add cells above, remove them, add cells below. You can copy cells and paste them. Another important thing you need to know is the fact that you have to execute the different cells if you want to calculate the result of it. So for a markdown cell, it doesn't really make any difference that you execute it or not. Well, it will not make any difference. So you can either execute it by clicking on this execute button. The language might be different in your case, or by clicking Shift and Enter as you just saw before, or Control and Enter. While the code cell is executing, you will see a star that appears on the left of the cell, and once it's done, it's replaced by a number, but we will see that just here. So once your Jupyter notebook is open, you have to start by loading the necessary libraries to execute the different functions that we will need. So let's do that. You can see the star here. You can see here the sun. And now it's a book, so everything is run and done. What we then need to do is to define a new Brightway 2 project and load the background database. And we also chose to work with the GEOENVI 3.6 database. So what you need to do is to have an account, an GEOENVI account, and access to this GEOENVI database in case you want to use that. Then you will need to go to the file section and download the database of your choice so that you can upload it here in this with these lines of code. So if I execute this one will simply initiate the Brightway 2 project. This is the name of the Brightway 2 project that you give. So it will load the lifecycle impact assessment methods and the biosphere metrics. This one will import the GEOENVI database. With this, you define a new additional database. So because now you will have the biosphere database, the GEOENVI database, and you need an additional one in order to be sure that you're not messing up the GEOENVI database. So this is the name that you will give to your user database. And in order to be sure that you're starting from fresh, clean database, it's better to reset the entire database and reset the parameters. So let's do that. And as you can see, I already executed this code before for this project so that the code was executed very fast. But in your case, for the first time, it might take up to 5 minutes because, as I said, it needs to load the lifecycle impact assessment method, the biosphere metrics, and the GEOENVI database. What we can then do is check the projects that we are working on and which databases are actually available. So as I mentioned, we are working in the protocol video test project, and we have 3 different databases: the biosphere, the GEOENVI, and our user-made geothermal database. So we are finally ready to start implementing the protocol. So I will spend a few words on the 5 steps. So first, we will start by defining the scope of the study. So which type of installation are we considering? Defining the system boundaries, defining the scope. Then we will develop a reference lifecycle assessment model. Ideally, we would have a modeling part and a validation part, but in this presentation, I will not spend a lot of words on the validation, even though it's a very essential part in order to be sure that the model you're developing is actually representing the reality well. From this reference lifecycle assessment model, we identify the key input parameters, so meaning the ones that explain most of the variability. Then we develop simplified models per each impact category that we choose. And finally, we finish with the summary and applicability domain of the different simplified models. Here again, you can see this whole part of validation for each simplified model, which is essential, but which I will not be showing here, since we are talking about a hypothetical installation. So let's go to the first step, which consists in the definition of the scope of the study. What we recommend to do is to find, for the category of geothermal installation that you want to consider, a so-called representative geothermal system. This is either a typical existing installation that really represents the type of installation that you want to have, or a hypothetical installation which uses average values obtained from a set of typical existing installations. This is a choice that you can make. Here, we will model a geothermal installation for heat generation with some direct CO2 and methane emissions, but no abatement system. The geothermal fluid is pumped from the ground, heat transferred through a heat exchanger to the district heating system before being re-injected into the ground. We use the European electricity mix for the electricity during operation and maintenance to power the pumps. And the system is in line with the GEOENVI LCA guidelines for geothermal energy that I mentioned at the very beginning of this presentation. So you can see that our system looks like that, but for this exercise, we will only focus on the modeling of the well drilling process and the electricity consumption. Then we need to make some LCA specific methodological choices. The functional unit, here we say it's 1 kilowatt-hour of heat. The GEOENVI database, well, we showed that already before. The life cycle assessment methods are also to be chosen. In the guidelines, we recommend we recommend 7 different impact categories. Here we will only be looking at 2, but it's just for the sake of the exercise. We can have a look at all the life cycle impact assessment methods that are available that we just loaded into our project, and you can see there are quite a few. And here we will focus on the ILCV 2018 impact categories of climate change and acidification. We can then either define the impact category directly using a triplet, so the name, ecosystem quality, and then the name of the impact category. So this would be the definition. Or we could look for the impact category among all the ones that are available by using a for loop. So we want to extract the one that has this in the name, climate change total, but not no LT. And this is to print it out. So if we execute this, we can see that we found the climate change total impact category. In Python, what is often used is also a so-called comprehension list. It's a more compact way to write down the for loop. So you could also say, look for all the methods in the Brightway method that have this in the string name, this in the string name, but not this, and extract the first element. So in Python, the numbering starts with 0. And you can see here too that we find the same. But well, let's keep just one and save both into this vector. Another interesting thing that we can do is look at the metadata, so the information of the characterization method that is behind. So you can see sometimes there is a description, the file name, the unit, which is very important, and the abbreviation and the number of characterizations. That's for the first step. So really defining the scope of the study. Once we have that, we can go to step 2, where the reference lifecycle assessment model is set up. So what we will be doing is we will describe this typical or this type of installation of geothermal installation that we want to model using different parameters. The inventory flows, they will be described with fixed or variable parameters by using scaling relationships or regressions between observed inventory flows and parameters, or in case of fixed parameters, typical values. So as mentioned in step 1, we will focus on the modeling of the well drilling and the electricity consumption. First, we will define all variable parameters and all fixed ones. Then we will define the activities that describe the different parts of the geothermal installation. And with those, we can assemble everything into the final reference lifecycle assessment model. So let's start with the parameter definition. Parameters, they can be either a numerical value defined as new float parameter, a Boolean value either between 0 and 1, or an excluding choice with this new NM parameter. And for each parameter, we can define the name or the label, the default value, the limits of the probability distribution. Well, this only applies for the new float parameters, the unit, the group, and sometimes the description. And we have different types of distribution functions that are implemented in LCA algebraic. They are defined with this distribution type code, and they can be either linear, normal, a triangle distribution, or a beta distribution. And you have here the description of how the limits of the probability distribution are used to define it. So we can now start to define the parameters that describe the well drilling. So the well drilling part consists on the one hand of the drilling platform construction, the drilling process in itself, and then the well testing. Let's assume that the drilling platform is simply described by its area. So we have we define a new parameter called a platform with the function new float parameters. This is the short name of the parameter, its default value, the minimum and the maximum value, the distribution type. So here we use the uniform distribution. Whether we want to assign it to a group, so it will be the drilling. Whether we want to give another label, the unit of this parameter, and its description. Otherwise, the inventory modeling of the drilling was based mostly on regression equations that were taken from this report. And I listed some of the equations below, and you can see that the parameters that pop out are the actual meters that need to be drilled, the well length, and a ratio between 1 and 1.5. So we can see that the actual meters drilled can be defined by the multiplication of the well length and the ratio. So that basically we need to define only two parameters. And then from this meter drilled, we can then estimate the volume of cement, the electricity for drilling, the mass of steel necessary, and the volume of drilling mass. So that's what we do here. We define the well length, the ratio between the meters drilled and the well length, the number of injection wells, the number of production wells. So here it's important to mention that the well length is the average well length. So we will just model one well drilling and multiply it by the number of injection and the number of production wells. Here you can see that the distance for the transport of the drilling equipment was set as a fixed parameter because it's known that the distance for the transport of the drilling equipment do not affect the environment, do not vary that much, and do not affect the environmental impact that much. So that's the decision that needs to be made. The same for all the parameters describing the drilling method, they were all set to be fixed parameters. Finally, we also have the well testing, which basically implies emissions of CO2 in the atmosphere. So we define another parameter with a distribution, a uniform distribution function that describes the amount of CO2 released during well testing. The other part then consists in the electricity consumption, because we know that during the operation and maintenance phase, we need to input electricity for the production and injection pumps to function. And the amount of electricity required can basically be described by this equation here. So it's the power of the production and injection pumps multiplied by the number of production and injection wells multiplied by the number of operating hours. So according to that, we define the power of the production well, of the injection well, and the operating hours are as new parameters with a uniform distribution function. Another important aspect, since I mentioned at the beginning during the definition of the scope of the study that our functional unit was kilowatt hour of heat produced, we need to estimate the total amount of heat produced. to be able to relate the environmental impact per kilowatt hour of heat produced. And the thermal output can be estimated with this equation. So the thermal output multiplied by or minus the yearly loss multiplied by the lifetime of the plant. And you can see here again, we define 3 different parameters. And I did not run all the cells, so let me quickly do that before. So once you have defined all your parameters, you can also list them here, where you can see the grouping they are assigned to, the parameter name, the default value, minimum and maximum values, the distribution, and the unit. So we have 11 variable parameters and 11 fixed parameters. Once we have that, we go to the activity definition. And here, maybe we are, or LCA practitioners are more used to talk about processes and exchanges. So activity is basically a synonym for processes, and exchanges here in Python is a synonym for flow. So the activity of well drilling, so the process of well drilling with drilling mud as exchange, which is the input flow, for example. What we can do is we can either use background activities directly. So for example, for the water use, but LCA and algebraic implements different functions to search for this database and find those background activities directly. If you execute this cell, you will see that it throws an error because on the one hand, it's case sensitive, so that's important to know. Here we ask him to look for all the values, all the names that start with water and have something at the end. But this function will look for just one match. And here it says that several activities are found with this name. So in case we are not exactly sure which activity we are looking for, so which process we are looking for, one should specify single equal false so that it lists us all the activities that start with this name. And we can then choose which one is the one that we want to use. So in our case, we have different background activities that we can use. So for the drilling platform, we will need concrete, the excavation and land occupation, steel for drilling, diesel for the drilling, the different materials for the drilling mud, the CO2 emission during well testing. And you can see here the difference between Find BioAct and Find TechAct. Find TechAct will look into the GEOENVI database, and Find BioAct will look into the Biosphere database. So here, when I execute that, I save all the activities into these names. But I also need to define some user-defined activities. So for example, the well drilling in itself, I cannot find it as such in the GEOENVI database. So what I can do is either create a completely new activity by using new activity, but in some cases, there might be that the building housing all the equipment that we're not modeling here, but is actually available in the GEOENVI, except that you need to modify some of the aspects. So what you can do is copy the activity and change some of the flows. But here I will only show how this function works. So let's say for the drilling platform, I create a new activity within our user-defined database, which will be named the onshore platform production geothermal tailor-made with square meters as units, and that uses per square meter 0.3 cubic meter of concrete, 0.3 cubic meter of excavation and land occupation. And I do the same for the drilling mud. So I define a new activity which describes my drilling mud. Using here, you can see the different parameters that we defined above. And then I also defined a new activity for the drilling well in itself. And here, the drilling well, you can see that it uses also some of the user-defined activity before. And for the amount, I have all the equations that I mentioned at the beginning when defining the parameters that were taken from the other report I mentioned. So now we have all the elements we need to finally create our geothermal installation. And here again, we create a new installation where we have the CO2 emitted during well testing, the drilling platform, the drilling well. As I said, we have 2 wells. So we have injection and production wells. So we just model one single well and multiply the activity by a specific by the number of wells that are present. And then we also have the electricity, which is required during operation and maintenance and estimated with this equation here. So this is our final reference lifecycle assessment model. And with PrintAct, you can have a look at how it basically looks like. And you can see here the equations that relate to the amount, the unit, whether it's a biosphere or technosphere flow. And as I mentioned, what we really need to do is to have our emissions per kilowatt hour of produced heat. So what we do is we create a new activity again, but this time which has as input the geothermal installation, but divided by the total amount of heat produced. And you can see basically the same. It's the same as above. Here. So this is now our life cycle assessment model. The next step consists in identifying from the 11 variable parameters that we had, the ones that are explaining most of the variability in the impact. So what it means practically is that we vary all the parameters defined in step 2 over their defined probability distribution. We look at the outcome of the LCA and we calculate the first order Sobol indices. So it's a global sensitivity analysis using Sobol indices. And the function of the LCA algebraic library interstochastic dashboard is what we are using for this stage. So it generates a specific number of Monte Carlo iterations, calculates the environmental impact for the chosen impact categories, as well as the first order Sobol indices. And the outcomes, you have a violin graph of the environmental impact, a cumulative graph of the first order Sobol indices, a heat map showing the importance of the first order Sobol indices, and the raw data that can be exported if needed. And you can see here that as input, I have my model. So the model per kilowatt hour. So this new activity that we created just here, the impact categories that we chose before, and the number of iterations that I chose. And here you can see those violin plots I was talking about, the mean, median, and standard deviation. So here it's climate change, and here it's acidification. You can see the impact variation. Here, the Sobol indices, and the redder the value, the most of the variance is explained by this parameter. So we can see that the thermal power output is a very important parameter, as well as the power of the production pump. And we can see a bit of difference in the importance of the well length between climate change and acidification impact categories. And then here you can export the data if needed. It will be exported as CSV file. So this was step 3. We identify the key input variable parameters. And what we can then do finally is to generate the simplified model for impact category. So the most important parameters are the ones with the highest Sobol indices, so the largest contribution to the variance of the impact. And using the function Sobol simplify model and specifying a level of variance one wishes to explain with the variable parameters, we can then generate the simplified model. So here again, you can see I use the Sobol simplify model function with our model and the impacts to consider. I set again the number of iterations. Here, this fixed mode tells the function what should be done with the variable parameters that are not retained in the final equation of the simplified model. Should they be set to median or mean values? Here by default is median. Min ratio is the minimum value of level of variance that one wishes to explain with the variable parameters. And the number of digits is the number of digits to display for the numerical values in the equation. So you can see here it's running. It's generating the simplified model for climate change and for the ecosystem. And you can see that for climate change, 3 parameters explained 80%, and for ecosystem, for acidification, it was 5 that explained 82%. And here you can already see a hint of the equation, but it can be displayed more nicely with this line of code. So here for climate change, and here for acidification. So we go from 11 different variable parameters to 3 and 5. It's quite a simplification. So then what we have is basically an equation, this one or this one, which describes using only those 3 or 5 parameters, the environmental impact in terms of CO2 equivalent or in terms of mole H+ equivalent for the acidification for the geothermal installation type that we defined at the beginning. So it's essential to finish this protocol with a summary of the applicability domain of the simplified model. And what we can also do is compare how the simplified models perform compared to the reference LCA model. And this can be done with this function where we have the geothermal installation per kilowatt hour, so the activity I mentioned at the beginning, the impact, and the simplified models that we generated. And what we will assess is how well both models match by calculating an Rsquare, which can take a value between 0 and 1 meaning a perfect match between both. And you can see blue is the reference model and orange is the simplified model. You can see that we have R-squares around 85% for both impact categories, and that the distribution seems to match. Again, here it's a hypothetical example. We do not go into a lot of details in the modeling phase, so it's really just more for the sake of the exercise. So as I mentioned, now we really need to be clear about the applicability domain of the simplified model. This applicability domain depends on the definition of the system boundaries and the methodological choices made in step 1, but also on the definition of the reference LCA model. So on the one hand, the distribution of the variable parameters, but also the values of the fixed parameters. So let's say that all the travel distances are around 20 kilometers, we might say, or 500 kilometers, we might say that the model is only valid for installations that are rather close to manufacturing sites, for example. But then what we can do is, if we see that our applicability domain is way too narrow or way too broad, we can still go iteratively adapt the different variable parameter ranges, or also the values of the fixed parameters. And as I mentioned already, missing from this demonstration is the comparison of the reference lifecycle model, but also of the simplified models with literature values. This is essential to ensure the representativeness of both models, and should be done as much as possible. It's sometimes difficult because literature values are not necessarily available, but it's very important to do. So the simplified models that are developed from this protocol, they can be very powerful to quickly estimate the potential environmental impact of geothermal installations of a specific type. The application of this simplified model requires first to identify a geothermal installation that matches the applicability domain of the simplified model, then determine the values of the parameters that are used in the simplified model. So in our case, for climate change, it would be the number of production wells, the power of the production plant, and the thermal power output. And then finally apply the equation. And you can say that as long as applied within the simplified model's applicability domain, and after careful checks of the representativeness of the reference and simplified models, the simplified models can be very useful to give first environmental assessment of energy generating technologies, in our case of geothermal energy technologies, and also inform the decision-making process towards a more sustainable society. Thank you very much. The script will be available on the GEOENVI website.